So, we are trying to prove that a certain limit exists. We had defined phi n g for a continuous function g in the interval minus r to r, and phi n g was the Riemann sum with respect to the resolution of identity. We are trying to show that the limit exists, right, which will be the integral of g with respect to the resolution of identity. So, we had started off the proof. So, let us continue. So, our aim is to show that if L is greater than n, phi L g minus phi n g goes to 0 as L n or n goes to infinity. Okay. If n goes to infinity, L automatically goes to infinity. So, let us do that. Let L be greater than n, okay, and we will look at phi L g minus phi n g. Okay. So, then phi L of g minus phi n of g. So, what is happening at each level is something you should understand. At nth level, we divide the interval minus r to r into intervals of length 1 by 2 to the n, right, and in the n plus 1th level, each of those intervals are divided subdivided into 2 pieces, and that is how you get 1 by 2 length of 1 by 2 to the n plus 1 and so on. Okay. So, this is something which you have seen in Riemann integration and so on. At nth level, you are dividing the interval into sub intervals of length 1 by 2 to the n. At the n plus 1th level, that is one more level going up, all that you are doing is each interval you had in the nth level, you divide that into 2. Okay. So, all of them will have length half of whatever was there already, right, whatever was there already was length 1 by 2 to the n, half of that is 1 by 2 to the n plus 1, right. That is how you get intervals of length 1 by 2 to the n plus 1 at the n plus 1th level. Now, here we have level n and level L, L is greater than n. So, to go to L, you have to do this several times, right. So, you go from n to n plus 1 by dividing the intervals into half once, then you divide it further, right, then you will go to n plus 2. So, that is dividing into 1 by 2 to the n plus 2 level and so on, right. So, you continue until you reach the length 1 by 2 to the L for each smaller interval. Okay. So, that and you have to compare these intervals and the value of g in these intervals and see that you can actually get the limit. Okay. So, let us write one step in full and then we will see how to combine these two summations. Okay. So, j equal to minus 2 to the L r to 2 to the L r, right, that is the definition. So, I am simply copying the definition, okay. There is nothing here, j by 2 to the L. I will have E j by 2 to the L minus the other end point, that is j minus 1 by 2 to the L, right. So, that is my operator, right, minus for n it is minus 2 to the n to r 2 to the n to r g by j by 2 to the n. Okay. So, maybe I should use k, so that there is no confusion here. So, I will put a k here and k by 2 to the n. Okay. So, that here it is a e k by 2 to the n minus e k minus 1 by 2 to the n, right. So, it is a I have just written the expression, I have not made any simplification. Okay. So, notice that L is greater than n, right. So, in the interval, so let us do that minus, so this is 0, let us say minus r to r, right. The nth level is dividing the intervals into length of length 1 by 2 to the n, right. So, I have smaller intervals. So, this length is 1 by 2 to the n. Okay. So, at this end point you will see that this is nothing but 2 to the n minus 1 by 2 to the n times r, right. So, next one will be on the numerator you add 1, so you will get 2 to the n by 2 to the n, that is simply r, right. The one left to this would be 2 to the n minus 2 divided by 2 to the n into r and so on, right. That is how you add. Okay. If L is greater than n, if L is greater than n, each of the above interval, each of these intervals. So, these intervals are of the length 1 by 2 to the n right now, but when L is greater than n, at the Lth level you want the intervals to be of length 1 by 2 to the L, right. So, you have to keep on dividing until you reach 1 by 2 to the L. Okay. So, each of these intervals get divided into 1 by 2 to the L length intervals. Okay. So, or intervals, so let me write this properly, into intervals of length 1 by 2 to the L. Okay. So, what do I mean by that? I take, so let us take one subinterval from here. Okay. So, a subinterval is going to look like j, let us say, let us use k, right, because we used k for n. So, k minus 1 2 to the n to k by 2 to the n, right. So, that is my subinterval. Okay. Okay, let us write this appropriately. Okay. So, this is the subinterval k minus 1 by 2 to the n to k by 2 to the n. Okay. So, that is one interval at the nth level, right. When L is greater than n, at the Lth level, this interval gets divided into smaller intervals. So, that each of them has length 1 by 2 to the L, right, that is what, that is the procedure. Okay. So, each of them gets divided into such that each subinterval has length 1 by 2 to the L. Okay. The length of this interval is 1 by 2 to the n, right. So, how many intervals will be there? There would be 2 to the L minus n intervals here, right. If L is n plus 1, that is the next step, then I have 2 intervals, right, because it is k minus 1 by 2 to the n to k by 2 to the n, I just divide into 2, just divide into half, equal half. But if I want to go all the way to 1 by 2 to the L length, then I have to do it 2 to the L minus n, I mean several times, so that I get the length, I get 2 to the L minus 1 L minus n subintervals of length 1 by 2 to the L there, right. So, if I multiply, I will get 1 by 2 to the n, right, that is the original length. So, that is all we are doing. So, at each level the previous the collection of the intervals in the previous level is divided into 2, right, that is how it is done. Okay. So, if you keep that in mind, you will understand the next step. So, we can write E k by 2 to the n minus E k minus 1 by 2 to the n to be equal to. So, I will write this in instead of bringing another notation, I will just write this in full, bringing all the, well, not all of them, but at least in full expression. So, this is E k, I have k by 2 to the n, that is one end point. The once I divide into intervals of length 1 by 2 to the L, the next end point here would be whatever is on the right hand side, you subtract 1 by 2 to the L, right. So, this would be minus 1 by 2 to the L, right, that would be the next the end point on the left, and left to that it would be again you subtract 1 by 2 to the L and so on until you reach k minus 1 by 2 to the N, right. So, of course, I want equality of this with whatever is written on the right hand side. So, I am only simply inserting the endpoints which I will get at the Lth level, right, I am cancelling them. So, I subtracted this particular one and I add the same thing E k by 2 to the n minus 1 by 2 to the L. Okay. So, I have not done anything except subtracting and adding the same thing, right, but these k by 2 to the n minus 1 by 2 to the L are the endpoints you will get when you look at intervals of length 1 by 2 to the L, right. So, the next one would be minus E k by 2 to the n minus 2 into 1 by 2 to the L and so on, right. So, plus etcetera etcetera etcetera, at the last I have E k minus 1 by 2 to the n, right. I hope this is clear. All that I am doing is I have one interval and I write that interval, I divide that interval into length its sub intervals of length 1 by 2 to the L. I collect the endpoints and then make sure that the difference between the endpoints of the original interval is written in terms of the difference between endpoints of the smaller interval. So, that they get cancelled, right, these things get cancelled each other and so on. Okay. So, telescoping sum. Well, what is the advantage of doing this? Now, this looks like exactly the decomposition with respect to L, right, except that the value of G for the k interval k by 2 to the n to k minus 1 by 2 to the n is the same for each of these sub intervals. Okay. So, hence, so keep that in mind, hence, so this is the key step, norm of phi L g minus phi n g. Okay. Well, what would be this? So, let us see. So, here if you look at, I have the nth level here, this is the nth level, each of this is, I have written it in the using j by 2 to the L and j minus 1 by 2 to the L, right. Those are the endpoints that will come up if I look at the decomposition with at the nth level. So, now the summation is same, summation is from minus 2 to the LR to 2 to the LR, except that remember these are G at k by 2 to the n's. Okay. So, for any sub interval that comes from here will have G k by 2 to the n there, but here these things are different, these are G j by 2 to the L, this is at the 2 to the L level, right. Okay. So, keep that in mind. So, let me draw that picture again. So, I have k minus 1 by 2 to the n and I have k by 2 to the n, this is what gets decomposed and I have k minus 1 by 2 to the n and k by 2 to the n, all divided into smaller intervals. Okay. This is of the length 1 by 2 to the L, right. So, at the nth level, so let us say this is the nth level. Okay. So, at the nth level I take the G value here, here, here and so on, right. But when I divide these intervals into those, at nth level the G value does not change, at the nth level G value is, so it is G by k by 2 to the n at all these points. Okay. But the E some endpoint minus E the other endpoint, they are going to be same, right, because I am going to use the same subdivision, right. So, what do I get? I get G at k by 2 to the n minus G at these points, right, times E minus E, right, at certain endpoints. But the difference is simply G at k by 2 to the n minus something else, where is that something else? Something else is actually in this interval, right, and this is going to happen for each k. So, I would be having terms like G at x minus G at y, right, but where are x and y? Well, x is k by 2 to the n, y is some point inside this. So, what is the difference? That is the distance from x to y, that is less than or equal to 2 to the by 1 by 2 to the n, right. So, I can take out supremum over mod x minus y less than or equal to 2 to the minus n, right. Remember that is what we did. So, I will show you that quickly. We took out this particular thing outside, right, because I had G that particular G by 2 to the n coming, j by 2 to the n coming in. When I subtract, I have G j by 2 to the n and something else, that something else is not very far, right, it is at a distance 1 by 2 to the n from j by 2 to the n. So, when I look at the difference, I have that difference of g x minus g y term, but the x minus y stay inside a length of in an interval of length 1 by 2 to the n. Okay. So, if you have understood that, you will see that phi L minus phi g, the norm of that is less than or equal to, from each of that I can take out this particular supremum mod x minus y less than 2 to the minus n mod g x minus g y, right, times well, whatever is remaining is the sum of those projections, right, they maximum add up to 1, right. So, that is norm of 1 which is 1. Okay. So, you will get this and well, this is for a fixed n, right. So, once you prove this, so I hope you have understood this, this will tell me, because of the uniform continuity, because of the uniform continuity of G, remember G is a continuous function on a compact set minus R to R, right. So, G is uniformly continuous. So, given any epsilon, I can choose a delta such that mod x minus y less than delta implies mod g x minus g y less than epsilon, right. So, because of uniform continuity of G, given epsilon positive, there exists n positive such that mod x minus y less than 1 by 2 to the n implies mod g x minus g y less than epsilon, right. So, apply that here, this will tell me that for mod x minus y less than 2 to the n implies g x minus g y is less than epsilon, right. So, that will imply that mod norm of phi L g minus phi n g is less than epsilon, right, for large n, right, because I want n such that, so this right, there is a delta, right. So, you have to choose an n such that 1 by 2 to the n is less than delta, right, that is what we are doing. Okay. So, this is true for large n and L is greater than n. So, by uniform continuity we have that this is a Cauchy sequence. Okay. So, hence phi L g is Cauchy in B of h. Okay. So, limit phi n g equal to phi of g exists, right, exists in bounded operators on the Hilbert space, right. So, B of h. Okay. Okay. So, that proves that the limit exists, but we still have to prove the properties, right. So, let us look at the properties. So, G going to phi g is linear. So, let us say one property 1, G going to phi g is linear, right. Why is that? Because G going to phi n g is linear, because G going to phi n g. So, remember what is phi n g? This is summation j equal to minus 2 to the n r 2 to the n r g at some point times the difference, right. So, j by 2 to the n minus e j minus 1 by 2 to the n, right. These are the operators and that is clearly linear in G, right, is linear in G. If I take G to G plus h, I will have phi n g plus h equal to phi n of G, right. So, phi n of G plus h equal to phi n g plus phi n h and so on, right. So, it will in the limit also it is going to stay as it is, right. Okay. 2. So, what was the second property? Phi of g star is equal to phi of g bar. Okay. This is true because, well, the same thing is true for phi n, right. So, because phi n of g bar, well, what is phi n of g bar? Let us write down the expression. So, that is j equal to minus 2 to the n r 2 to the n r g bar of j by 2 to the n, right, and whatever remaining is self adjoint projections, right. So, E j by 2 to the n minus E j minus 1 by 2 to the n, which is its own adjoint, right. So, this is simply equal to summation j equal to minus 2 to the n r 2 to the n r. I write it as g j by 2 to the n E j by 2 to the n minus E j minus 1 by 2 to the n, and I take the adjoint of that, right. So, because it is adjoint, all I am doing is taking complex conjugate of G, the other one is self adjoint, right. So, this is nothing but phi n G star, okay. And then if phi n G star converges to phi G star and phi n G bar has to converge to phi G, right. So, that will prove that phi respects the star operation. So, that is the second one. Third one we just proved, norm of phi G is less than or equal to the supremum norm of G, because we already know that, right. For we have proved that norm of phi n G, in fact we proved a slightly better estimate, but as n goes to infinity this is going to be a issue, right. So, let us just write L infinity norm of G, okay. And the fourth one. So, fourth one we need to prove that phi G h, so it is an algebra homomorphism, phi G h equal to phi G into phi h for G and h continuous functions on minus R to R, right. This is true because it is true for phi n G and we are taking the limit in the operator norm, right. This is true because it is true for phi n, okay. We will prove this. Okay. So, let us see how to prove this. So, we need to show that at each nth level, right, phi n is multiplicative, okay. So, recall that, okay, we will need one more page perhaps, okay. So, recall that, let us write down the expression for phi n G again. So, this is summation j equal to minus 2 to the n r to 2 to the n r, right, G at n points, that is j 2 to the n, E j by 2 to the n minus E at the other n point which is j minus 1 by 2 to the n, okay. Phi n h is going to be an expression of the same kind, okay. What will happen if I multiply them? Okay. So, look at phi n G times phi n h, okay. So, these two expressions, so let me quickly write them, j equal to minus 2 to the n r to 2 to the n r, both are at the nth level, okay. So, E j by 2 to the n minus E j minus 1 by 2 to the n, okay. So, this is one times the next one summation j equal to minus 2 to the n r 2 to the n r h at j by 2 to the n E j by 2 to the n minus E j minus 1 by 2 to the n, right. So, I have not done anything except writing down the expressions. So, phi n G times phi n h, well you just multiply them, right, these are linear combination of operators, you simply multiply them, but when you multiply you remember that these are projections, right, E j by something and so on, these are projections, and you also know that when I multiply these differences where the intervals are disjoint, you are going to get 0, right, because the range is ranges are orthogonal, right. So, recall that range of E A minus E B is orthogonal to range of E C minus E D, okay. If the interval let us say B A, so I wrote it in the wrong direction, but that is okay. B A is D C is empty, right, or singleton. right. Even if A and D are same intervals, same points, you will still get them to be orthogonal to each other. Okay. So, the ranges are orthogonal. So, the ranges are orthogonal would also mean that the product is 0, right. So, E minus into E c minus E d is 0. Okay. And if they are same, since these are projections, you see that it is E a minus E b. So, check that E a minus E b whole square. So, they are self adjoint and they are projections, and remember the p less than or equal to q implies p q equal to q p and things like that. Those results about projections p less than or equal to q implies 3 assertions, right, that we had proved, and that is applicable to E a and E b, right. E a, if I write E a minus E b, that means A is greater than B, and so range of E b is contained in range of E a and things like that, right. So, and E a minus E b, well, you already know that is the projection to the orthogonal complement of range of E b inside range of A b, right. So, this is equal to, so well, I do not need to check that because this we have already done. So, E a minus E b square is equal to E a minus E b, because E a minus E b is the orthogonal projection, is the orthogonal projection onto whatever is remaining in range of E a, but perpendicular to range of E b, right. So, it is looking at range of E b, you look at its orthogonal complement, that is inside range of E a, right. So, remember that A is bigger than, right, that is why you look at E a minus E b. Okay. So, so when I multiply phi n g and phi n h, the different intervals, when I multiply the corresponding projections, I will get 0. When the intervals are same, the endpoints are same, the product will give me exactly what it is, right. So, all that will happen is these g and h gets multiplied, right. So, it follows that phi n g times phi n h is simply summation j equal to minus 2 to the n r to 2 to the n r, I will have g j by 2 to the n times h j by 2 to the n. Any other 2 points when I multiply, I am going to get the 0 for the corresponding projections, right. So, it is a 2 to the n minus e j minus 1 by 2 to the n, right, which is the definition of phi n of g h, right. So, phi n g into phi n h is equal to phi n g h, hence it follows that phi of g h is equal to phi of g into phi of h, right. So, phi is going to be a, so phi the map phi is from continuous functions on minus r to r, which is the support of the, or the support of the resolution of identity is contained in minus r to r, and phi from here to b of h is actually is a star algebra continuous homomorphism, right. Right. So, that is what we get from. So, all that we have done starting from a resolution of identity, we managed to look at these Riemann sums and prove that the limit exists. Okay. So, that is going to be the integral with respect to the resolution of identity. So, we will stop with that, let me give you that notation. We will use the notation phi g equal to integral of g with respect to the resolution of identity E t. Okay. So, we will stop with that. Let me also give you a reference, so that these things are clear. okay, reference. Look at the book by Barry Simon. So, all that I am going to do in the next few lectures will also be from the book by Barry Simon, Operator Theory. Okay, so, this is the fourth in a series of books. Okay, so, fourth in a series of books in analysis. Okay. All right. So, we will stop here. We have proved that if I have a resolution of identity on the real line, it is possible to define the integral of that with respect to integral of a continuous function with respect to this resolution of identity, as long as the resolution of identity is supported in a compact interval like minus r to r. Okay. What we are going to do is we will write down various versions of the spectral theorem for self adjoint operators. We have the, so we have seen some of this earlier, there will be some repetition. The aim is to show that all these versions, so using the resolution of identity, using the version that it can be realized as a multiplication operator, and there is a continuous functional calculus, etc., all these versions are going to be equivalent to each other. So, we will prove that they are all equivalent to each other. If I prove one version of the spectral theorem, I can get all the other versions of the spectral theorem. Along the way, we will also prove that the spectral measures that come up. So, if you remember in the version where we realize the normal operator or the self adjoint operator as a multiplication operator, there was a measure space, right. What if I change, what if I get a different measure space and I get the realization for the same operator, what are the relations between these two measures? We will study them as well. Okay. So, we will stop for the time being.